Let's now talk about the Java implementation of insertion sort and also try to argue about its running time and also how to trace it. Let's now do all of them. And as usual, that's the conceptual reminders about this kind of sorting algorithm actually works. I'll leave you to that. And this will be the Java implementation for insertion sort. And it turns out to be also nested loop. However, it may look trickier than the selection sort because we got a while loop over here. And before I let you pause the video, I would like to give you one hint about how you may think about or how you may actually imagine how the insertion sort is supposed to work and why it will be consistent with the conceptual workings that we discussed in the earlier part, right? I want you to look at this while loop over here, the inner loop. And we know that this Boolean condition here over here, as long as it remains true, we're going to keep executing the body of the while loop. That's the definition for the while loop. And by the way, the indentation over here for these two lines suggests both lines should be the body of the loop. Of course, to be precise Java code, you have to put the curly brackets. I just want to save some space on my slides. But if you look at the source code I made available to you, you will see the curly brackets around these two lines as the body of the loop, right? Just to point it out to you. And answer this question over here. Under what circumstances as a Boolean condition will the while loop exit and stop executing the body of the loop? That's my question for you. And you should really derive that particular Boolean condition by using maybe some logical rules that you learned in your logic course. All right. And now you can pause the video and think about it. All right. Assuming that you thought about how this insertion sort implementation in Java might work, let's now try to trace it together. Okay. And that's the Java code over here. Let me now go directly to the question I posed to you before you pause the video, which is under what circumstances will this particular while loop exit, right? And we know that as long as this condition is actually true, it's going to keep executing the body of the loop. So when we actually say exit when, it's going to be when this particular condition evaluates to false. Logically speaking, let me just use the logical symbols that you learned from your maybe 1019 course or maybe 1090. It's going to be not the case that this particular conjunction is actually true, right? So that'll be j larger than 0, and that's a conjunction a at index j minus 1 larger than current. I'll just say c just for short over here. So that'll be the condition under which we're going to exit from the loop. Let's now try to do a little bit more distribution. I'm going to distribute the logical negation over the conjunction. And there's something called De Morgan, which you learn in your logic course, right? If you got any trouble, you can let me know. So that's going to be j less than or equal to 0 is going to be the negation of this or the negation of that, right? So we're going to change from conjunction to disjunction. Or a at index j minus 1 less than or equal to c, right? If you somehow recall what I said when I talk about the conceptual workings for insertion sort, we're going to look at the correct spot in order to insert the inserted element so that the sorted version, the sorted portion remains sorted. And we're going to keep trying until we actually see the current element is actually smaller than or equal to that particular element to be inserted. And this corresponds to that. Okay, you can actually rewind the video about what I said earlier. Anyway, this condition over here is very important. So let me highlight it. Okay, so this condition is something that we're going to look at that when we actually try to trace, right? All right, so let's now talk about the tracing. Okay, and as before for the selection sort, I got two boxes over here. The outer loop, which will be over here, right? It's the outer loop. I actually got some box over there. Let me just say blue over here. The outer loop. So that's what I have some intuitive description about. At the end of each iteration for the outer loop, what can you expect to be achieved? And also we got the inner loop over here. And for the inner loop, let me just highlight it using pink over here. Okay, so that's the inner loop over here. Actually, that becomes orange. So let me just put you see my point, the while loop over here. All right. Let's now try to trace the code. Okay, and now I would like to do a little bit more like a larger number of iterations to trace to really show to you how insertion works. It's actually quite important, right? We really want to show that the implementation itself is consistent with the conceptual design that we proposed, that we actually presented earlier. All right, let's now start with I. The loop counter is going to be starting to be 1 over here, right? So the first value of I is going to be 1, okay? And then we're going to execute this line over here. So the current is going to be assigned to AI. So that means A1. A1, we know that it's going to be the value 1 over here. So that's the value that we're considering over here, right? Just 1 over here. And then we're going to go for this inner while loop. Basically, it is going to keep somehow shifting. You can see AJ is assigned to AJ minus 1. Think about what it's trying to do. For example, if AJ is this, AJ is assigned to AJ minus 1. That means copy this into over here. That means we're shifting somehow elements to the right. Right? That's basically what we're doing. Right? Okay, let's now take a look to see exactly how to do it. Okay, and we're going to keep shifting element to the right until either J is actually reaching 0, meaning that we cannot shift anymore, or the current element that we're looking at is actually less than or equal to C. In that case, we know that will be the correct spot to insert. Conceptually, that's what's happening over here. All right, let's take a look. All right, so what we're going to do is we're going to say J. By the way, J is assigned to be I, right? So that's just keep in mind. So we're going to start with J will be starting from index 1 over here. And then, so now we want to compare J minus 1. J minus 1 will be this particular value over here, right? J minus 1, right? And then AJ minus 1 larger than current, is that true? 3 larger than 1 is actually true. In that case, we're going to execute these two lines, in which case we're going to shift this element conceptually to the right by 1 position. In that case, we're just going to replace this element over here by 3. Right? You might be wondering, well, if we replace it, what happened to the value 1 that's being overwritten? You don't have to worry because that's already stored in the current variable over here, just in case you're worried. All right. So after this, we're going to decrease the J by 1. So that means we go for the next one, right? And then in that case, we're going to run the loop again, right? Should we do another iteration? We're going to see if AJ minus 1 is larger than current. AJ minus 1 in this case will be actually J is already decremented already to 0. So that means 0 larger than 0 is going to be false, right? Or when J is less than or equal to 0, in that case, we're going to exit from the loop. So we are done, right? So there's only one iteration, which I just described, that we only shift the 3 into this position over here, and then when J is decremented to 0, we exit from the loop. There's no further execution for the body of the loop, for the while loop. Okay, just be careful. And then don't forget, we gotta write back the current that we just overwritten, right? So what's going to happen is we're going to have so this will be actually this part over here will be outside the while loop. Just be careful. So that's a part of the outer loop. So AJ in this case, because we already decremented J to be 0, so that'll be the current value for J, and then AJ will be current. Current is actually equal to 1, right? So that's going to be actually 1. Quite a bit of working over here, but I'm going to trace for a few iterations so you can see. But that's exactly what you need to do, I'm afraid. There's no shortcut. Before we move on to the second iteration, let's now recap what we have achieved in the first iteration. And you could definitely refer to this box over here. So let's now read it. At the end of each iteration of the for loop, the outer loop over here, and A will be sorted from A0 to AI. And the same interpretation as the selection sort box. So this we're talking about the I value before I plus was executed, right? So at the end of the first iteration, you should really consider I being 1 rather than 2. Okay, it's important. One thing I also want to mention, in this particular implementation of the insertion sort, in the input array, we talk about the very first element being constituting being the entire range for the sorted portion already. Okay, and so that means after executing the first iteration, we will grow this sorted area by just one element by inserting 1 into the correct place. And that's exactly what we did, right? Remember at the, when we were tracing the first iteration, we actually tried to insert 1 into over here and then put 3 over here. That's basically what we did. So effectively, this would be the sorted portion of the array after the first iteration. And now if you check the blue box over here from A0 to A1, right? A0 to A1, this will be the green area that's actually being sorted. Okay? That's something you really want to understand conceptually. And something I forgot to put, what about the J value? When we actually put the J value at line number 8 over here in the first iteration, J should be exactly over here, right? That's what we said before. When J reaches 0, in that case, that's about the time to really exit from the loop. Or think it this way. If J reaches 0, that means the element that you want to insert will just become the minimum in the sorted area. In this case, the 1, right? You can see 1 just becomes the minimum of the sorted area. The sorted area contains 1 and also 3, right? 1's the minimum. That's another way to look at that. Okay, that will be 0. All right. Let's now move on to the second iteration. For the second iteration, I will be incremented from 1 to 2 to begin with, right? And before that, what will be the array to start with for the second iteration? Let me put it down just for cleanness. It's going to be 1, 3, and 4, 2. And of course, just remind ourselves, this will be the sorted portion to start with. We can expect that somehow we're going to insert 4 over here into the correct spot, into the sorted portion, so that these 3 elements over here is going to become the new sorted portion at the end of the second iteration. That's what we'll see. All right, let's now take a look to see how this is done. And what we'll see is we're going to execute this for loop again. And then what is the current? Current is going to be AI. AI will be A2. So A2 is this 4 over here. That makes sense. So that'll be A at index 2. So which will be the value 4. All right. And then we're actually going to now try to execute the while loop. And don't forget, J will be initialized to be the value of I. And so that means J will actually start with I being 2. So that's where J will actually start from. And then we're going to keep comparing A at index J minus 1. Okay. As long as it is larger than the current, we're actually going to keep executing the body of the loop. Right. So now, current is actually 4. 4 larger than 3. Oh, sorry, let me say that again. Sorry, I was saying the opposite. As long as A at index J minus 1, in this case, A at index J minus 1 should be 3, right? Because J start to be this index over here, right? A at J minus 1 should be this one here. As long as this J minus 1 index elements is actually larger than current, 3 larger than 4 is not the case. Or you can think about 3 less than or equal to, 3 less than or equal to the current, which is 4, is actually the case. That means we're going to exit from the loop right away. All right. If we execute from the loop right away without ever executing this part of the loop, so that means the newly inserted element just becomes the maximum of the sorted portion. Right. That's something you want to keep in mind. And then we're going to go to the outer loop again. So we just go here, and then we're going to reassign AJ to be current. J never changes. J remains to be over here, which will be 2. Right? Just remind ourselves. It's going to remain 2. And then we're going to override it by just current, just by itself. But let's just do it anyway. So 4 will just be overwritten by just 4 itself. Right? In that case, we have effectively grown the sorted portion by just 1 element over here. Right? And if you check the blue box once more over here, and before I++, at the moment, I is simply of value 2. In that case, from A0 to A2, they are sorted. Indeed, from A0 to A2, that's a sorted portion. So we got 1, 3, 4. And let's now move on to the last and third iteration. What's going to happen is we're going to increment, first of all, the value of I from 2 to 3 to start with. And then let's now put in the array over here. It's going to be 1, 3, and 4, and 2 over here. And then you can see this is the sorted portion over here. You can expect that at the end of the third iteration, we're going to somehow insert 2 into the correct spot, maybe over here, into the array. And then after that, we can effectively grow the sorted portion to cover the entire input array, and then we are done. All right. Let's now take a look over here. Let's see here. We're gonna execute the for loop for the third time. What about the current value? The current is gonna be AI. I will be 3, so AI will be A3. A3 is actually going to be this value over here. It's going to be 2. All right, and then we're going to execute the while loop for the third time. And don't forget, J initially will be just value of I. So we start with this. And then we're going to keep comparing A, J minus 1 against current. Okay, so the first one to compare will be 4 against the current, which is 2. Over here, right? So now 4, over here, let me say it again. So 4 over here, larger than 2, right? 4 over here is AJ minus 1, and 2 over here is the current. So 4 larger than 2 is actually true. So that means we're going to execute this particular part over here. That one there is simply to do the following. It's going to say AJ is actually going to be assigned to AJ minus 1. Let's do that. So it's going to say AJ over here is going to be assigned to AJ minus 1. So this part here is going to be replaced by 4. And don't worry, because 2 has been stored as a current. So we still have that value. It's not being completely overwritten. All right. And then after that, we're going to say J minus minus. So now J will be pointing to this spot over here. All right. And then we're going to go back to the while loop once more, and then we're going to compare AJ minus 1. AJ minus 1 is now going to be 3 over here, right? And then compare that with the current. So AJ minus 1 is actually 3. 3 larger than 2, the current is actually true, right? So that means we're going to execute this once more. We're going to make some spot over here. So what's going to happen is, so AJ minus 1 is this element over here, and that one is larger than current, so we're going to say AJ is assigned to AJ minus 1. AJ is currently over here, is going to be replaced by AJ minus 1. So 3 will be over here. Okay, and then we're going to also decrement J by 1. So J is actually going to be over here, right? There's a decrement that we see. All right, let's now go further. And when we try to do another iteration for this while loop, so now J is over here, index 1, right? And then J minus 1 is actually going to be the 1 value over here, right? And now let's try to see. AJ minus 1 is actually 1. 1 larger than current, which is 2. False. 1 larger than 2 is definitely false, meaning that we're now ready to exit from the loop, right? So that means we don't really decrement J any further. So this will be the final value for J upon exiting the while loop. So this will be just 1. All right. And when we try to execute this part over here as part of the for loop, the outer loop, AJ is assigned to current. AJ, A1 is assigned to currents. Current will be simply just 2, right? So we're going to put 2 over here. Magically, you can see 1, 2, 3, and 4, and we have effectively grown the area of the sorted portion to cover the entire array. So we are done, basically. Right? It's a tricky tracing, but I'm somehow confident that it was clear as I could be. And then I really say, really, you want to do the tracing also by yourself to really completely understand exactly how this works. I know it's kind of tedious and also very easy to get lost, but that's the only way to train yourself to understand exactly how nested loop actually works. I will encourage you to do so. All right. And finally, you can see by the at the end of the third iteration, before I++, you can see from A0 to A3 is completely sorted. It will be 1, 2, 3, 4 over here, right? Okay, what about the running time? Let's talk about the running time very quickly. We're going to do something very similar to how we did for selection sort about loop counter pattern over here. Right, let's now try to put it over here. For the let me put it here. For I value right? You start with 1 all the way to n minus 1, right? For the iteration. So that'll be 1, 2, 3, all the way to n minus 1. That'll be the I value. What about the j value? Remember, we only talk about worst case when we analyze the code for runtime, right? So now if you look at that, j is actually going, well, let's say what the worst case to really execute a loop would be, you only try to exit the loop when j reaches 0, right? That's how you can think of it. So this will be the worst case for the while loop to exit. Worst case in terms of the number of iteration that we have to execute, right? So j is going to be I, and the worst case will be when it's actually equal to 0. So that means the j value is going to be from I down to 0. So that'll be 1 and then 0. And then it's going to be 2. You know, let me just draw a little bit better. I think it would be better to draw this way. And j value will be from 1 down to 0, and then for the second iteration it's going to be from 2 down to 0, and then from 3 down to 0, right? You can see why I'm doing this. It's kind of the opposite way for the triangle. And for this one over here, it's going to be from n minus 1 all the way down to 0. Right? What about for every iteration for the while loop, the inner loop? You can see this part over here is simply big O of 1, right? So this part over here is definitely just big O of 1. That's obvious. And we're lucky because for when j is equal to 1, when j is equal to 0, for every one of them, it's going to be big O of 1. So we can discard that. It's going to be a lower term. That will be dropped ultimately anyway. And what about other parts for the outer loop, for loop? The while loop over here is just one statements as part of the body for the outer loop. We got another one over here, another one over here, another one over here. Each one of them over here, this one here, this one here, and this one here, all big O of 1. Let me just write it down. This line over here is big O of 1. Line number 3. Line number 4 is also big O of 1. Line number 8 is also big O of 1. So we can also discard it. Ultimately, what we need to write down is like this. So big O of the running time. You can see for the very first, when I is equal to 1, we got 2 iterations for the inner loop. So because we got j value being 1 and 0, so that'll be 2 and then plus. This when I is equal to 2, it's going to be 1, 2, 3, right? Plus 3 and then plus 1, 2, 3, 4, 4 plus all the way to, and in the very last iteration, you'll be from n minus 0 down to 0, right? You can definitely calculate from 0 to n minus 1. How many numbers in between? N minus 1 minus 0 plus 1, which would be n, right? That's something you can definitely calculate aside. And there will be, for sure, a arithmetic sequence over here from 2 all the way to n. And that will be, if you do the math, big O of n squared. Okay, you know how to apply the formula. I'm going to skip that particular step over here. That will be big O of n squared. And it will be, not surprisingly, just the same as the selection sort as we actually predicted when we talk about the visual, the abstract description for selection sort and insertion sort that we did earlier, right? You can see analyzing the running time on the conceptual sketch over here versus analyzing the runtime on the actual code over here give us the same result. You should know both. All right? All good. Let's now go back to the slide to see what else to be set. Right, so that's about the insertion sort. If you complete it, that's exactly what you will see over here. I think somehow I just put 1 over here, but it doesn't really matter, if there's extra term over here. But you can definitely see the exact working for the insertion sort. Okay. All right, so that's the conclusion is the insertion sort is also a quadratic time algorithm. All right.